Let me introduce you to my Warco drill press. It's got a 650 watt motor, Morse taper 2 spindle, and we've got a travel on the quill of about 80mm. And under this cover we've got two belts configured with an idler to give 16 speed range. And we've got the usual rack and pinion adjustment for the table height. So all in all, a very powerful, robust, sturdy drill, ideal for hobbyists. But could it be improved? Well, in common with all drill presses of this style, changing the belts can be a bit of a pain. In this particular model I've got to go up the ladders, undo the screw on the cover, then adjust all the belts, change the speed, tension it all back up again, and then I've got my new speed. And when I want to change the speed again, I've got to repeat it. But could it be improved? Also, like all drill presses of this style, there's a little bit of free play in the quill. It can be tightened up with this little set screw that runs in the groove, but could it be improved? When you move the table up and down, you lose your reference to your hole and you've got to get back on the centre again. Particularly apparent if you drill a pilot hole and then you put a large clearance hole in, or if you want to drop it down even further to tap a hole. But could it be improved? Let's find out. Okay, so that's the basic idea. So there'll be a steady system on here that will run on rails that holds the quill in place at the bottom end, and then essentially an XY table like you'd find on a knee mill. Oh wow, so you're building a milling machine then? No, it's not a milling machine. But it's got a milling style table? Yeah, I know. It's not a milling machine though. This is going to be a drilling machine. So what that will enable me to do is to drill very accurate hole patterns using the table, or bore holes, counter bores, and then there'll be a slow speed feature for tapping threads. So that's the idea. It's a precision drilling machine. You sure you can't mill with this machine? It's not a milling machine. Well, for a start, you've got the wrong bearings in here. These bearings are just to take the axial load, not any radial loads that you get from milling. And the second thing is, when you're milling, because there's a helix there will be a tendency to pull whatever you've got in here, in this case the chuck, out of the taper because there's no drawbar holding it in. So it's a precision drilling machine, not a milling machine. Although, if we took the spindle out, made a new spindle with a drawbar, automatic tool changer, and the right bearings. No, this is a precision drilling machine project. Let's just get that done and get it finished. But you could mill with it. Leave it. Okay, so let's have a more detailed look at this machine. So you can see an XY table towards the bottom there. It runs on those linear rails, and that's moved up and down by the gold handle, crank handle on the right. Then we've got the quill itself. You're going to see move up and down. That moves up and down on those linear rails. That moves up and down in the usual way. There's the black 3-pronged handle that moves that up and down. It's just supported at the back on those linear rails. As you can see, I haven't drawn all the quills, so there's a little bit of a gap there, but hopefully it gives you the idea. Okay, we'll just zoom out a little bit and spin it around so you get a better view of the table. So the table itself is a fairly traditional XY table.
I haven't drawn the way covers on there, but you can see some of the shields and the guards that are getting ready to take those bellows type covers. Otherwise it's fairly traditional XY table. You've got the two handles to move it in the X and Y direction. The other handle you can see on the top right on that tall beam is the handle to actually move it up and down. I'll show you that mechanism in a minute, but this is essentially the table moving up and down on those linear rails. As I say, a little bit like a knee on a traditional milling machine. And then if we spin it around to the backs and then zoom in so you can see the mechanism. So that handle on the blue column, you can see there's a drive shaft that goes all the way through, and then the two purple parts are bevel gears. So they're 45-degree bevels, so they take that rotary motion and turn it onto that ball screw, which is a kind of salmony coloured part, and that turns that ball nut up and down. The ball nut's connected via a small arm onto that table. So a little bit like you would find on a normal or benchtop milling machine, certainly. That moves up and down like that in that slot. Also, while we're around the back of the machine, you can see the main tube there, that kind of white column. That's about an 80mm main column. Then there are 3 clamps that clamp these side rails onto that, kind of blue side rails that go onto that. And they then take a plate on the front. That will be a precision ground plate, and then that takes those linear rails, so they are 20mm rails. Now we're onto the front control panel, so I'll make this control panel from scratch. You can see there's an on-off button and the speed control, then the forward and reverse, and then bottom left is emergency stop, and then the 2 arrows for up and down jogging. Here you see I've taken that front panel off, and you can see how I'm going to make it. So there'll be 4 tubes, one at each corner, and each of those tubes will have a slot machined in it to take a panel. And then in the panel at the rear that bolts onto the machine itself, there'll be grooves that those panels sit in, and the same thing on the reverse side of the outer panel. You'll probably see when we get around to making that part, but that'll just be made in sections and then slid together and bolted up tight. Okay, so let's zoom it around a little bit more so you can have a look underneath that, the table, the XY table, and then you can see the Z locking out mechanism. So that's that purple, sometimes called a Bristol clamp, but it's an indexable clamp that you can move the handle round and ratchet it round, and that goes on to, because you don't want to put pressure on those linear rails, don't want to clamp those direct, but it locks up against a kind of T-nuts, that green one there. You can see it slides in that slot, and it locks that cylinder in place, the white cylinder, so the blue part can't go down any further, but they're not directly connected, if that makes sense. Then you can see the XY table just makes use of standard high win 20mm rails and carriages, and it moves in the X and Y directions. There's no covers on here, but you can see well, you can see the drive handle there. I think that's where I'm going to lock it out on the drive handle end, stop it moving, sort of simulating a stepper locking it out. There you can see where the way covers would go. I haven't drawn those yet. The bellows on that side, and then there'll be another set at the rear there that will go from rearward, be folded up, and then go upwards towards the quill, a bit like you'd see on a regular milling machine, just to keep the worst of the swarf out from going down onto those rails. So that will fill in that whole area there, and also cover for when the quill goes up and down. The last thing to mention is that we've got standard T-slots on the top there for bolting the vice down and fixtures and so on. Looks ambitious. Shh.
So I've had this drill press quite a few years now. One of the first jobs I did when I got it was to add this digital readout on the quill. It's really handy if you just want to put a counter bore just to a precise depth. It's a pretty fast update, works really well. So all I did is made another bracket that runs off the back of this existing depth stop, goes to this multi-axis rose joint here, another one at the other end, and that pulls the read head up and down. By using those multi-axis joints top and bottom, it allows for a very slight bit of misalignment without putting pressure on the head. So I bought this from a company called Machine DRO based in the UK. They sell a lot of nice high quality gear. This has got a really nice smooth quick update and it works really well. Okay, so if we take the front control panel off, and inside we've got a no volt release switch here, so if the power fails then it turns this unit off, saves it starting accidentally. At the top there we've got the rocker switch that controls the light. We've got a couple of ground points there, so there's 4 cables in total. So one will be the mains coming in, one of them will be going off to the safety switch, because in the lid up here, if you open the lid to change the belts, it cuts the power. One of them will go to the motor itself, and one of them will go to the light circuit. Okay, now we've got the cover off, I've labelled up all the cables here. So we've got 4 cables in total. This first one here, this comes from the mains. This one over here is from the motor, or to the motor. This one here is for the light, you can see it's a smaller cable. And then this one is the lockout switch. There's a safety interlock on the cover, so if you open the cover to change the belts, the motor won't run. Okay, so looking at it a little bit more closely, so we've got our main cable coming down there, onto the mains, onto this one, which is on pin 1. If we look on our little box here, this is the back of the safety switch. So 1 comes in here. If you press the switch to run the motor, that joins it across to 2, terminal 2, and 2 is up here. There we go. 2 is up here, and that goes to the lockout, so that's the safety lockout on the cover. Assuming the cover is closed, then that comes back on pin 4, which is down at the bottom here. So it's gone all the way around 1, jumped across there, gone up to the lockout, back into 4. That does 2 jobs. One, it energises the coil, and you might just be able to see there's a relay coil in there. That's the interlock system, so as long as there's power going to the system, it will hold the power, hold the switch in, and if the power cuts, then it switches this off so it doesn't start inadvertently when the power goes back on. The other function of pin 4 is when that's joined across there, it feeds power into pin 3, and pin 3 is here, and that goes off to the motor. This is just a single phase motor at the moment. Comes back from that motor down this cable and into the neutral and back into the mains. Now there's 2 earth leads on there, one's from the mains and then there's another earth here, just making sure the basic chassis is earthed as well. So essentially that's it. The only other function you've got on there is there's a feed off the live that comes to here that goes up to the switch, and when you switch that, so that's this little switch at the top here, switch that switch across, that goes from here to this one. You can see these are a lot smaller, so that just makes that connection across there. That goes through this cable to the light, and then back from the light back to this common neutral connection here, back into the mains neutral, and that's it really. Okay, so we'll be using almost none of that. In fact, we won't be using the mains because we're going to run that to the inverter. We won't be running the motor because that will run off the inverter. The lockout, if we use that at all, that will go to a safety inhibit on the VFT control cabinet, so we won't be using that. The light switch, we won't use that because we'll wire that on from the inverter control unit. So the only thing I think we'll run from here is probably the earths. So let's have a look at how we're going to power this drill press. So we're going to use this inverter here. So this was sent to me free of charge by Banggood to include in this video, and we'll have a look at it and see what we think. This particular model is an XSY81. It's good for 2.2 kilowatts and 12 amps of current. Now the reason I went for this particular model, well, a couple of reasons really. One, it's extremely cheap. This is somewhere around 55 or 60 pounds. The Hyungyang model I've got on my CNC machine was around 100, and a few years ago a name brand Siemens model I bought was about 350 pounds. So these are certainly extremely affordable, so let's see how we get on with it. So in terms of a very, very quick overview of what we get here, we've got the control panel on the front. This is removable, and you have the usual little ribbon cable at the back there. So you can extend this and have the panel mounted somewhere else, somewhere on the front of your control box. So we've got that. And then at the bottom here we've got an access panel. This is where the main wiring goes in. So we've got the knockout panel there to put the wires through, to give it a little bit of protection. and then down the bottom there you can see left to right. So left, that's first one is the earth, then we've got neutral and live, and then the last three are for the motor. So they are for UVW, that's where the three-phase motor goes. So that's what you've got at this end, and then at the other end this is where all your signalling's done and the controls for external controls and inputs and outputs. Now on this particular model it's really hard. You might just about be able to see the labels on each one. I've just soldered this header on just slightly off to one side. Oh, you can almost see just there. So I'll probably have to make a note of those somewhere else so I know what they are. Might help if I pull this gasket out a little bit. That's what you got at the top end, so that's what we've got there. That's what we've got at the base. And then on the rear of the unit, we've got the usual little small fan that blows over the heatsink to keep the thing cool. These can be a little noisy, so we'll see if we end up using that or have an auxiliary or something like that. And what else can we see? If you look inside the unit, we can see the big capacitors there. Looks like it's a transformer for probably for dropping down to the low voltage. And then not easy to see, just through there you can see on the back of the heatsink the IGBTs. No, not easy to see. That's the part, they're the switches that you want to keep cool. Okay, so that's a very quick overview. We'll go into detail a little bit later, but so we've got our mains power coming in there, motor there, all our inputs and output signals if we need to use those for any remote controlling, and then we just need to make sure we mount it so that we got enough airflow across there, and that's kind of it. That's our basic introduction. So that's the inverter. Now Banggood also sent again, we'll show these now, but we'll go into them in more detail probably in the next video. But Banggood also sent a load of components for the control box. So we have cooling fans. These are the switches for these are for the jog buttons. Yep. So I've got 3 to do the jog because I think I need to use 2 of these back pieces on one of them. We'll have a look at that a bit later. Our 3-position switch, potentiometer for the speed control, filter there, so we'll put a line filter in front of this because these are electrically very noisy. That will go in. Emergency stop. This is our on-off switch. So this is a momentary on-off switch. So it just briefly makes contact as long as you hold that down. And the reason I went for that is because we're going to have a latching relay for the emergency stop safety system. So that's the power. A couple of these 12-way connector blocks just to make life a little bit easier for some of the wiring. You can't buy these individually, so we've got a pack of 10 for next to no money. These are the volume or speed control. That will be the speed control knob that goes onto the potentiometer. And I was getting a bit low on the heat shrink. I like using heat shrinks to make a neat job, so they sent me a pack of that as well. Alright, so all these will be part of the control box. We'll show that probably in the next video. So what we need to move on to next is what we're going to connect this up to. So the next thing we need to look at is the motor, the 3-phase motor. And in the end, and I went for this one. It's quite heavy. So this is a 1.1 kilowatt motor, which is why I went for the slightly larger inverter. Because of that, it's a 90 frame motor. So the frame on my drill press, the 650 watt, is an 80 frame. And what that basically means is that the distance between, the spacing between these feet is larger on this. The input shaft over here, or the output shaft over here, is larger, as is the keyway, as is the distance between this and the front of face. Basically, it won't fit on my drill press as is, so I need to make an adapter. So the reason I went for this was, which is almost twice the power of my current drill press, was I wanted plenty of torque at low speed. I wanted to definitely be able to do some tapping, and just in case, I don't think he's listening, but just in case we ever turn this into a milling machine, a 1.1 kilowatt motor will come in very handy. I knew it! You're making a milling machine, aren't you? Okay, so the other features of this motor are, so this is a 90S frame motor, so it's slightly larger than the 80 frame. What that means is instead of the 19mm shaft, you get a 24mm shaft on here. It's a little bit further between this point and this front face, but that means the pulley that we've currently got on the drill press won't fit. But that's okay. I think we'll go for a taper lock pulley anyway. I just need to work out exactly what size I'm going to go for. In common with a lot of these type of motors, you can move this electrical connection box, or effectively move it around to different sides by indexing the feet around, and those are just two separate machined features that bolt on, so you can index those around and effectively move this to different positions. Now if you look around the back here, it's this is a TEFC, so fully enclosed fan that's just onto the back of the shaft, the non-driven end, and just blows air constantly over that motor and keeps it cool. That's one of the things to watch out for. So if you're running these below the nominal, this is 50 Hertz we're going to run this at. If you're running them below the 50 Hertz, then of course this fan's going to run slower and slower, and it will be a kind of exponential drop off. So if you're not careful, it'll quickly overheat, so you need to do something about that. So there's a couple of options available. We'll get into that a bit later. I'll just talk a little bit about how these work, just as an overview in principle. They are quite amazing really, and it's amazing to think what you're getting for your money. So what we're essentially doing, we're converting, in our case, single phase AC through this unit, and we're turning it into three separate phases that we can use to control the speed of this three-phase motor. So there's quite a few little steps involved in between, and just very brief overview of how it's doing that, because some of that might be useful when we go to see the parameters. We can refer back to this and get an idea about some of those features and what it actually means. So we start off with the main supply going in. So we've got our, in the UK that read 230 volts AC, that goes into the inverter, and then inside there we got the full bridge rectifiers, so we're rectifying that signal, so it now looks crudely something like that. There's our rectifiers there, and then that gets smoothed by the capacitors, so now we're looking something like that, a little bit of ripple on it. So that's our capacitor bank there. And then that goes into the IGBTs, so we're now DC, so we're firing that into the IGBT. So they are solid state switches, so we referred to those a little while ago when we were showing the cooling at the back there. So those are the things we need to keep cool. So those go through a range of these. I won't draw it actually how it is, but they're just banks of these switches like that. And effectively what you're then doing, so they output from there, and they then go into the motor. So let's just draw our three-phase motor here and run the motor. And what these are actually outputting is, well, let's just draw them as sort of representations. So they're sine wave like this. So there's one of the phases. Second one shifted by 120, badly drawn. Another one shifted by 120. So that's 120 and plus another 120. That way, notionally. So they're sort of shifted like that, and that's what goes into the three-phase motor, into the windings and the different poles, and spins the motor around. But actually you're probably thinking, well, how do these switches actually make sine waves? The answer is they don't do that. It's PWM. So if we just break out of here a moment, instead of it being like that, so if we think about our sine wave, and we'll draw it best we can freehand, and what they're actually doing is doing something called PWM, pulse width modulation. So if we take a time reference, that's okay, just very rough. So we'll take that, and what we end up doing is breaking this signal down into how high that level is as an analog level. So here it's 0, so nothing happening, and we get to this point here, it's kind of halfway. So in that frame nothing's happening, and this frame is kind of on for quite a lot of the time. When we get to the top here, in this frame it's on all the time. Oops, it's not higher. because don't forget these are PWM signals that are the same voltage. Then we go down the other side and it's on for half the time. Keep want to draw it half the level. Sorry, right. And we get all the way down to here where it's hardly on at all, so a little spike like that, and then 0. Then we go the other side and it goes the other way. So we've got a little bit like that, on briefly and then off, and then on for a bit longer, then off, then on all the time. Badly drawn, but hopefully you get the idea, and so on. And those are a fixed level as well. So we're turning this motor on and off rapidly and for longer and longer periods of time in any given time interval, such that it's fully on when it's here, and then it's fully off when you get to this point here, and then the negative can go the other side. So this is PWM, and that is what's going into the motor into each of these 3 phases. Now normally when you run something on a square wave like that, it's horribly noisy because this sudden jump in voltage here puts a massive pulse into the system and can make nasty noises. So servos and stepper motors, if you run them at a very low step rate, can be quite poor. But we get away with it in this case because this induction motor effectively smooths out a lot of this, and it actually runs very smoothly. In fact, induction motors are noted for running relatively smoothly. So that's an overview of what we've kind of got there. And it's worth just talking about that because this little interval of time that we've got each of these pulses over is one of the parameters we need to refer to in here when we go into some of the parameters in depth with a little bit of tuning. So we'll come back to that in a minute. That's our delta T, or our carrier frequency. We'll come back to that in a minute. But that's a step by step what's actually happening. So we've got our AC mains coming in here, rectified through the full bridge rectifier, then it gets smoothed out, then we're onto the DC bus, and these get switched on and off rapidly by the IGBTs, which are in here. And we create our pseudo sine waves with the 120 phase, or 120 degrees phase difference between each of the 3 phases, and that runs the motor. But we're actually running it via PWM control. That's a very quick overview of what's going on. Can't leave it like that. Okay, I'll just quickly draw these in. Yeah, it's better. The first thing we need to do is wire this up, just make sure it will turn on before we go any further. Just helps a little bit if you magnetize them. And the last one is the earth. So this is just temporary while we make sure it works. Alright, so we've got live is brown in the UK, then neutral is blue, earth, green and yellow. That's fine. I'll just make sure these are tight. I don't know why, just don't like them being loose. Right, there we go. Okay, now we'll plug it in and let's see what happens. Hopefully it'll be a few seconds delay while the capacitor charges up and then it will come on. Actually, a year or 2 back I did have one of these. It was a Hunyang one, not this make, and I did just this. Just live and neutral and earth. You can't really go wrong. Plugged it in, switched it on, a second or 2 later, massive blue flash, bang, and the whole thing was dead. And I got into a bit of a debate with the eBay seller about, well, I even sent in the photos, I haven't even connected the motor yet, I've just wired it up and it's gone bang. And in the end I did get my money back and I went for another one. Right, here we go. Hopefully that won't happen. So we'll turn it on. This is genuinely the first time I've done this as well. Let's see what happens. Okay, no blue flashes, no sparks. I did think the fan might come on, but it might... Okay, on this model then, the fan might only come on when we actually are in run mode. Okay, that's not so bad then. Oh, I guess it could even have a thermocouple on it, but if it only runs when it's actually powering the motor, then that's great, because it means if we're filming or whatever, and it's just idle, we don't need to worry about that. Right, that's a good start. Okay, well, good. Next is, let's get the motor wired up. So we'll switch this off, and we'll wire up the motor next. So if we have a closer look at the motor plate on the side there. Okay, so as you can see on there, I'll run at either 50 Hz or 60 Hz, so we've got 50 Hz in the UK. Now this is a 4-pole motor, so that means that it will run at about 1420 or a little under, allowing for slip. It's 1.1 kilowatts. And with that configuration, so it will run nearly 5 amps, 4.7 amps. So we're going to, because we're 230 in the UK, we're going to run it at 230 volts, and we'll do the delta configuration. It also has the option of doing the Y configuration down here if you're running it at 400 volts. If you do that, it runs at lower current, so you're still getting the same power output. There's a few other things on there we don't need to get too worried about, but you've got the IP rating, the waterproofing rating 55 is pretty good. The insulation class for the windings F is pretty high, so it's quite a nice little unit. It's nearly 14 kilos, so it's pretty heavy. So that's a quick overview of the 3-phase motor that we've got. In fact, it's actually repeated. Oh, there we go. It's actually repeated on the lid as well. So we're going to be doing the delta on the left there for the 230 volts. Okay. Okay, now we're looking inside, and you can see the windings of the motor that go into here, and we're going to put our motor power supply into here and connect onto those. So we just got to configure this. I didn't ask for it, but the other thing we got in here is a little block here. So that's likely to go to an auxiliary device like a thermistor or something like that. And here's our links. We've got our links across, so let's see how many we got. Oh, go on then. Click. Before we go too much further, just thinking about the orientation of this on the machine and where I'm going to want the electrical outlet relative to the feet. I'm going to swap things around a bit, so I think we need to move the motor plate around to the other side and put the feet here, and then maybe I'll have a look, might even turn this 90 degrees. But let's get this off first. The other thing is this doubles up as quite a nice little nuts and bolts tray to prevent losing them. Think of everything. There's a close-up of the motor plate. I'll say, so far I'm really impressed with this TEC company. Total engineering commitment. Well, you can't argue with that, can you? So it's just held on with these cap head bolts here, look like M8. If you guess? Yes. Quite tight. Okay, let's note which way around they go. A single hole to the front and on the outside. Right. I guess I could always look back at the video. See if they got any thread lock on. No. No, they were just tight. On the feet here now. That way. So with the feet mounted at the bottom, that's going to be up on the machine. The wall will be behind here, and then down is sort of that way. So it would be nicer if the cables come out the bottom there and then loop round into the inverter that way. I mean, here for a start, it's going to make it awkward to put that bolt in. So we'll just take this top off, index it round, have the harness or the cable run coming out the bottom there. Alright, now just being careful not to move that or catch it. To show what we got under there. So, got a nice gasket to keep the worst, the water and chips and stuff out. And then here's our housing. You can see we haven't punctured the gland yet. And there's an auxiliary there, so if you're running this heater or a thermistor or whatever, then that can come in there. Right, so that needs to go around there. So I got hold of this spindle cable. This is the one off my CNC machine, so it used to run the water-cooled spindle, the 1.5 kilowatt water-cooled spindle. And like all of these glands, they've got like a rubber cup at the end, so as you do this up, it's tapered and it holds onto the cable. Okay, so if you've made it this far through the video, I'm sure you're already aware, but I'll just mention it anyway. If you need to reverse the rotation of these three-phase motors, you just swap any pair of cables. So you can swap these two over like that, these two, or these two, whichever you prefer. Or it's probably a little bit easier to do at the inverter end. So you've got the three at the inverter, just swap any pair over and it will reverse the rotation. And the last connection to make is the earth. So they provide you with this little earthing point inside here. There's also one on the motor. Just about see it in shot. Yeah, there's one down there as well. If you wanted to earth it that way, but I think it's more convenient to earth it inside the control box. Okay, so we've wired up the three phases, and we're doing it in the delta configuration for the 230 volts. We've also got the earth connected, so that's all good. This is a shielded cable, by the way, because there's a lot of electromagnetic noise off these motors, and we'll ground that in the control box at the star earth. The other thing you'll notice in here, I think I mentioned it earlier, there's a temperature sensor here, and this varies its resistance depending on so the hotter it gets inside the motor windings, the higher the resistance. And you can hook them up through this connector here to a special kind of relay designed for these that goes in the control box. And when that temperature gets too high, about 150, 160 degrees, it will trip, and then you have to arrange it so that that little relay system connects to your emergency stop on the inverter via one of the digital channels. So it's probably the neatest way to do it. So it's probably worth explaining that a little bit further. There was no data sheet for the PTC, so the thermistor that's used inside the motor, that was supplied. So I phoned up the motor supplier and said, could they send one? So they have emailed it. This is the spec sheet for the sensor itself. So they use these PTC, positive temperature coefficient thermistors, so they're measuring the temperature, and there's basically two types. There's this one if you've got a single phase motor, or in our case we've got a three phase, so we've got one for each of the phases. And the way these work is, so we've got the triple PTC series down here. So in the workshop at the moment, say around 12 degrees C, so it's pretty cold, and I measured about 200 ohms across the terminals. So we're clearly working in this range here, and this is in the, that's for 25 degrees, but it's not really that in the workshop at the moment. So we're somewhere in that range. And then there are three kind of trip points to be interested in. One is at 5 degrees below the trip point, one's 5 degrees above, and one's 15 degrees above. And basically the resistance goes from this relatively low value, so 1650 ohms, just as you go into the trip point. When you get to that trip point, or just over it, 5 degrees over, it shoots up to 3990 ohms, and then just 15 degrees over is 12 kilo ohms. We look at that on a graph, it looks like this. So when we get to this trip point, which is here, the resistance suddenly shoots up. So what we need to know is the value of the temperature at which this trip point is happening. Now the way they do that, or code for that, is if you look at the wires on the terminal, they were blue, blue. So if you have a look at what blue, blue means, we get to here. Blue, blue means that this particular PTC gives this rapid rise in temperature. They all give this same resistance change, but it gives that particular rapid rise in the resistance, sorry. In other words, it's got this shape at 130 degrees. So they've all got the same shape, they all have this same resistance trip characteristic, exactly the same resistance. It's just that they do it at different temperatures depending on what the rating of that motor is. So we're running at 130 degrees, blue, blue. So this curve for us will happen at 130, and the resistance will suddenly shoot up from 1650 to 3990. So that kind of means in principle you can connect it to any of those relays and they'll all suddenly detect this change around 3.5 kilo ohms, and that's when they'll trip something out via one of the normally open or normally closed contacts, depending on what facilities they've got, and some of them might even self-reset and so on. So that's, if you're interested, that is the data sheet that came with the three-phase motor. I'll hold it there so you can have a copy of that, just for your interest. Thought you might want to know that. So we've got the motor end done. Let's bring in the inverter. So now we just need to connect up the UVW. They're the three phases, and these are already labelled because I labelled them last time when I used them on my CNC spindle. As I said a moment ago, these may not be correct and I may need to swap these around to get the rotation correct. If so, I'll redo the labels. We will connect up the earth to this pin down here, or this terminal here. But ultimately when it's in the control cabinet, everything will come down to a star earth, probably something about here, where all the earths come together. But just for running now, we'll do that. And then the shielding, we'll earth that to that same star point as well. That's an interesting point on these. I think as hobbyists, we generally do this pigtail style and we'll come off like that. It will obviously be covered, but we will terminate this kind of shielding like that and put it to an earth. And my personal experience is that works perfectly fine. But if you look at all the name brand inverter manuals, they'll tell you absolutely not to do this, and that you're supposed to get a kind of clamp that goes all the way around 360 degrees with metal teeth, and it picks up on this shield, and then it keeps that earth going into the metal of the control box and to the earth ground plane that way. I assume that's to do with the way that the very high frequency sort of skin effect maybe of the radio waves, or the high frequency signals that are going backwards and forwards here, maybe the way that they're supposed to spread out rather than going into this. This is probably a poor connection for very, very high frequency, but I don't know. I'm not a sort of an EMC expert by any means. This seems to work, so I'm going to use it again. If I have any issues, I'll look into see if I can get the actual proper connector on here. Okay, let's get started on it. It's just a simple type. This won't be the final installation. So there we go. So we've got the earth from the power coming in and the earth from the spindle body. Then we got neutral, then live. So that's very difficult to film. Then we've got the UVW from the motor. And that's, in terms of powering the in and the out, that's technically it. At this point you could do a mega ohm check, so a sort of 500,000 volt check for the insulation, and check you haven't got any leakage. I just don't own that kind of equipment, so all I'm going to be able to do is a very basic continuity test, and we'll literally just check if the earths are all connecting together. So we've got the earth pin here, which is the largest one. No surprise, that's okay. So that's coming in okay, and then out to the motor body. Yeah, it's there. Oh, didn't get across the paint. Okay, so got there. Yeah, okay. The shaft. Okay, so that's looking pretty good. Well, there's nothing left to do other than plug it in, see if it fires up. Okay, 3, 2, 1. No bangs, good. Okay, and the final thing to do is to configure the parameters in here so that you can talk to this motor and it knows what it's looking at. So we need to know things like number of poles, minimum maximum frequency, minimum maximum voltage, the speed range we want to run at. We need to know where we're going to run our start and stop from, the control. Also things like vector control for torque control and things like that. And I think about 127 parameters in total, and we're going to deep dive all of them. So we're going to do all that on the next video. Hopefully you enjoyed following along so far, and I think this is quite an interesting project. Next video we'll look at the parameters. We'll also take a look at the control box that goes on the front of the drill press itself. Right, see you on the next video.